So in the vector space model, we have used the TF-IDF term weighting to represent the contribution of the individual terms in a document. Note that the ultimate target is to assign a score to all the documents in the collection for a given query. And what we have discussed in vector space model is we will be representing all the terms in the document D, say, as some weights, or there will be some weights we will be assigning on all the terms in this document, and correspondingly we will be doing the same for the query as well. We will be assigning some weights to the individual query terms, and we will be computing their vector similarity. Particularly the cosine similarity that we have seen is the most robust one, or I mean relatively the better one as compared to the other similarities, for example the Euclidean distance or dot product, which we have seen. Now if we follow this term frequency, inverse document frequency term weighting in the vector space model, we have seen that the term overlap is basically considered basically this term overlap is basically indicating the presence or absence of a term from being contributing towards the scoring of the document or not. If it is present, it will be non-zero. Then only it will be contributing some score into the score of the document. And for absence, it will be basically 0. So log of 0. So this entire term will be becoming 1. We can also define it in a way so that it will be considered as 0. Now there will be a scenario, or there will be some you can say some need to keep it as 1. Let me discuss this. So let's say a term Q is not actually appearing in the document. So its term frequency will be 0, right? Term frequency will be 0 if the query term is not occurring in the document. The term frequency of the term, the query term in that document will be 0. But sometimes it is needed for smoothing purposes, which will be discussed later, to have some weights assigned to those situations as well. This smoothing can be considered as the IDF smoothing here, or the collection smoothing. In that case, we will be basically considering the occurrence of 0 occurrence as 1 due to this. But in general, for the time being, you can consider if the term is not absent, not present, basically if the term is absent in the document, we can directly consider a 0 weight. Later on, this smoothing and all will be discussed during the discussion on language model. So presence or absence will be based on the term overlap. Term appearing more in the document gets higher weight due to this factor. So basically this is the term frequency factor, and this is the inverse document frequency factor. First occurrence is more important due to this log, because as we have said, if we do not use this log, it will be a linear function, but we need a sublinear function. For that, we have introduced this log, which basically indicates the first occurrence is more important, the second occurrence is a little bit less important, and so on and so forth. So at any point, a later presence of the term is not that much considered that much important as a first occurrence. So if a document is containing one term twice, the contribution of the individual two terms will be much more than if the same term is occurring in another document, say 20 times. So the weight of the term in say D1 will be something say X, and the weight of the term in D2 say Y. Of course, if the term frequency of the term in D1 is greater than the term frequency of the term in D2, then of course this will be implying, or we should be assigning more weights to the first document, that is D1. But note that, let's say it is 2 and it is 20 and it is 2. Then basically the term frequency is 10 times larger in case of document D1, but this will not be. So basically I can generally say term frequency of T comma D2 is equals to 10 times the term frequency of the same term in the document D1. But this will not be implying, using this log normalization or this sublinearity, the weight of the document will not be, document 2 will not be 10 times the weight of D1. So the contribution of this 20 occurrence will not be, of course it will be greater, but the 2 occurrence. So if, let's say, for the sake of argument, let's say for this 20 occurrence, the individual, I mean, if we average the individual term contribution of this 20 occurrence of the term T, it can be say 0.1. Let's consider it say 0.1, 0.1, 0.1 for the 20 terms. For that same term, in this, the term, the importance can be say more than 0.1. It can be say 0.5, 0.4 and something. So this is the beauty of this log linear, this sublinearity using this log function. The rareness of the term is basically taken care of by this factor, which is basically the IDF. And we have seen that it is biased towards longer document. So a longer document will be getting higher score due to different factors. We have discussed this in the last class. So in this vector space model, there is no notion of relevance. What we have seen is basically it is only considering the overlap. There is no notion of relevance here, and the relevance can be a very uncertain process. That is, a document can be considered as relevant from some certain perspective and non-relevant from some other perspective. So as such, we are only considering the term overlap. There is no notion of relevance here. At this point, let me tell you this, all the, I mean, except for certain recent models, all the presently available retrieval models based on this assumption. But still, in the probabilistic model, we want to basically put some notion of relevance into the actual retrieval model. But again, as I am saying, most of the retrieval models presently, or all the retrieval models that we will be discussing in this course, are based on this. In fact, the relevance model that we will be, or the relevance based, or the probabilistic model that we will be discussing will also be considering this. But the foundation of the probabilistic model is basically to model the relevance of a document for a given query. So probabilistic model is basically the mathematical formalization for the relevance and non-relevance of a document for a given query queue. So basically, the concept of a probabilistic model is to model the inherent relevance or non-relevance of a document using the IR, or information retrieval process. Now, this process can be very uncertain, and we know, and as I said, the uncertainty can be from different perspectives. For example, a single document can be considered as relevant from the topicality and can be considered as non-relevant if we consider its publication time, right? So for example, if I read the bulletin, the COVID-19 bulletin that is prepared or circulated every day, every evening by the Indian government. Today is 17th. So if I consider the 17th COVID report, it is relevant. But now, if I on standing on 17th of February, if I get the report of 15th, topically it is relevant. But from the recency, it is not the recent one. This is the most recent one. So that's why it can be non-relevant. Now, there are uncertainties, and probability theory is the best tool for us to actually handle this uncertainty. And as a what we'll be basically proposing is basically called probability ranking principle, which states that if we are given a retrieval system, a retrieval model say R, the response to a given query Q to a user who had submitted this query Q is a ranking of document of the collection in order of decreasing probability of relevance. So if a query is submitted to a relevance retrieval model R, and if the retrieval model is producing an output which is basically a set of documents in the decreasing order of probability, where these probabilities are estimated as accurately as possible based on the data that we have, then the overall effectiveness of the system will be the best. It seems very intuitive. Let me again tell you, repeat the concept. So basically, if we have a retrieval system, the retrievals, the performance of the retrieval system will be the best when for a given query, it will be producing a set of documents D1, D2, D3, and so on, when their relevance are basically ordered in the same order in which they are being produced. The relevance of D1 is the most, relevance of D2 is the second most, and so on. Mathematically, we can say estimates the probability for all D in the collection C as accurately as possible. That means the estimated relevance of a given document will be close to the true relevance of the given document, right? So this is the first factor, where the probabilities are estimated as accurately as possible. And the second factor is this: rank the documents by the probability of relevance. Sorry, the second point is basically this. So the retrieval model, the performance of the retrieval model will be the best if this is the case. If the relevance or the estimated relevance of the first document is the most, followed by the second retrieval, second ranked document, followed by the third ranked document, and so on. Note that here R is basically an indicator, a Boolean indicator, indicating whether the document is relevant or not. Okay. So if we get this from a retrieval model, note that I have specified the retrieval model with R earlier. Here R and that R is basically different. Here I am just talking about a retrieval model RM. And here R is basically a binary indicator of the relevance. Graphically, this can look like this. Imagine information retrieval as a classification problem, where given a query, we have a defined set of relevant document and a defined set of non-relevant document. Now, basically the size of the circles are intentionally kept like this, because in any standard collection C, for any query, the number of relevant document will be a fraction of the fraction of all the documents in the collection. So in other words, the number of non-relevant document will be much more than the number of relevant document in the collection for a given query. Now, given a document, it can be having either the probability that the document is non-relevant, or it can be the probability associated with the probability that the document is relevant. Basically, probability of relevance given the query and probability of non-relevance given the query. That is, it is indicating whether the given document or the document under consideration is belonging to this set or this set. So, considering the probability, this PRD and PNRD should be summing up to 1, and a document should be specified as a relevant document if and only if this probability is greater than this probability. Now, using the Bayes rule, probability of R given D can be considered like this: probability of D given R into probability of R by probability of D, and probability of NR given D can be extended using the Bayes rule as this. Now, again, from the classification point of view, a document will be considered as relevant if this is basically greater than this. In other words, this portion is greater than this portion. In the denominator, it is the same. So that's why they are being cancelled. So what we'll be ending up with basically PDR divided by PD given NR, that is basically probability of the document given relevance divided by probability of the document given non-relevance is greater than probability of non-relevance by probability of relevance. Now, what is this? Probability of relevance and probability of non-relevance. This can be considered as the prior probability of a document being relevant. Now, having a collection C containing, say, 1 million document, we can simply consider them uniform. Considering them uniform, it will be cancelling them, basically 1 and 1. So it will be just classify a document as relevant if probability of DR is greater than probability of DNR. Now the goal is to, for every document, we need to estimate this probability of D is relevant to the given query Q. So it can be mathematically written as either this or this or this. Probability of R equals to 1. Here R is basically a Boolean indicator variable which can be either 0 or 1. 0 means non-relevant, 1 means relevant. So probability of R equals to 1 given the document and the query, that is, we are observing a relevance given that particular document and the query. This can also be written as probability of given relevance provided the document. It can also be simply written as probability of relevance given the document. Now here you can see from here and here we have excluded Q because Q will be being considered for all the documents, all the DIs in the collection, right? Now if we continue, let's say considering this notation here, so probability of R equals to 1 given D again can be extended by the Bayes into this formula. And similarly, the probability of non-relevance can also be specified as this. Here R equals to 0 or R equals to 1 or 0, they are basically again considered as the priors. So in the probabilistic retrieval strategy, we'll be estimating these probabilities using a simple model called binary independence model. This model assumes that the relevance of each document are independent of the relevance of other document, which is not actually true. Why? Because let's say we are given, say, 3 documents as output. Let's say first document is the repetition, or no, let's say this is D1, this is D2, the second document is D2 and third document is D3, and say D2 is basically duplicate of D1. Now, although from topical point of view, D2 is equally relevant than D1 as D1, but considering the ranked nature, if we are provided with this ranked list, as a user we will be first reading this, then we will be reading this, the second document, and on reading the second document, we have already all the knowledges that are present in the second document, which we have already consumed from the document D1. So the relevance of each document is actually dependent on the other documents, but in this binary independence model, it is basically assumed that they are independent. And it is also considers a binary relevance, that is, the relevance can be either 0 or 1. That is, a document can be either relevant or non-relevant. There cannot be partially relevant or highly relevant. This kind of grading will not be there. A document should be either classified as 0, that is non-relevant, or 1, that is relevant. Now what we need to do is we need to order the documents by the decreasing probability. Now again, in the binary independence model, binary here in this binary independence model, binary will be another notion of binary is basically the presence of the individual terms will also be considered as independent. Not sorry, that is basically the independence assumption. So basically the terms occurring in the document will be not dependent on any other document, any other terms in the present document, which we have seen is not actually true. For example, the San Francisco or Hong Kong example that we have seen. And binary means a document will be basically considered as an document incidence vector that we have seen during the discussion on the incidence matrix that we have used for Boolean retrieval. Now note that we have again come to the Boolean retrieval strategy, but we are essentially will be doing something not actually Boolean retrieval. There will be some ranking here as well, but here binary is indicating that each document can be considered as a vector, where this n is basically all the terms in the vocabulary, and the individual component of the vector of the document will be basically some term weights. It can be TF-IDF, it can be something else. But here in this binary assumption, we'll only be considering them as 0 and 1. That is, either a term is present or not. So in the binary independence model, the query will also be considered as a term incidence vector. Now for each document D, we need to compute probability of R, that is relevance, given the query and the document. Now instead of computing this, what we'll be doing is we'll be replacing Q by the vector of Q, and we'll be replacing the D by the vector of D. Now this is the notation of vector, so you can see they are actually different. It is in bold and this is in simple italics. So we will be computing the score based on probability of relevance given the vector of Q and vector of D. Now what we'll be doing is we'll be using an odds ratio. Odds ratio of observing relevance given the query and the document will be basically, odds ratio will be basically probability of observing the relevance given the query and the document divided by 1 minus the same thing and 1 minus probability of relevance given the query and the document is essentially probability of non-relevance given the query and the document. So they are basically the same in the denominator. Now if we extend them using the Bayes rule here, it's simple. We can simply extend them. This is basically using the Bayes. In the denominator, this will be cancelling each other. So here what we'll be ending up with, probability of R equals to 1 given Q, probability of R equals to 1 given Q as numerator and denominator, and in the other part we will be having probability of D, that is the document under consideration given the relevance and the query, divided by probability of the same document given non-relevance and the query. Now, can you say here I am actually cancelling this part? Can you say why? Anyone? Anyone? Please try. Because there is no document factor here. Our ultimate target is to specify a ranking or to produce a ranking. If we simply exclude them, the overall score will be different, but the ranking will be remaining the same for all the documents, right? So that's why that is excluded. Now, using the independence assumption, which is basically stating that the presence of the individual query, individual terms in the documents are independent of each other, we can simply extend this document based on the individual component of the document. That is, it was a vector. Now we have extended it based on the individual component of the vector. Okay. Now here, let's say, so if n is, as I said, n is the total number of unique terms in the document, in the vocabulary. Now this product is over this. Now a term can be present, so you can actually understand that the vocabulary will be containing many terms, but all those terms will never be occurring in a single document, because a collection is basically a set of documents, right? And sometimes, say, some sports related terms will be present in the sports related document, some politics related terms will be present in the politics related document, and so on, right? So there will be some factor like when the term is present in the document and when the term is absent in the document. So this is extended like this. The numerator is basically considering breaking the things up, where the term is present in the present document and when the term is not present in the present document. Similarly, the denominator. So if we replace this thing, that is the probability that the term Ti is occurring in the relevant document, if we replace it by Pi, the corresponding 1 minus Pi will be the probability that the Ti is not occurring in the document, that particularly the relevant document, considering R equals to 1. So it will be basically 1 minus P. Similarly, if we specify or denote P Ti equals to 1, given R equals to 0Q, R equals to 0 means it is indicating a non-relevant document. So probability that Ti occurs in a non-relevant document, if I specify it as Si, the corresponding 1 minus Si will be probability that Ti not occurs in non-relevant document. This can be denoted like this. This is its confusion matrix, the same thing in the tabular way. So following that, the probability would look like this, and that can also be extended to consider only this part. So this, I mean, if you work on this a little bit, if you think about it a little bit, you will be understanding that here what I am doing is essentially I am considering the occurrence of the term in the document separately and all the other term occurrences separately. So this is for the terms which are occurring in the document, and this is for the terms which are not occurring in the present document. Now extending, here I have introduced this part, which basically will be cancelling. That's why I introduced this, and I have ended up with this, where I'm actually excluding this. Again, I hope you can understand that this is only considering the terms which are not present in the document, but our target is to rank or score the document under consideration. So that's why it can be reduced to this. So the final scoring function will be, so it is basically a product. So in computer science or in information retrieval, you will be understanding that product is not actually always a good option, because sometimes if either of these product has become, or either of these value is becoming 0, the entire value will be becoming 0. So that's why it is a general practice of putting a log and then basically coming up with a summation. So we know that log AB will be basically log A plus log B. So instead of scoring based on AB, we'll be applying a log before it and we'll be breaking up in this way. So now if practically this PI is considered as a constant in this scoring formula. Generally, it can be considered as 0.5. And SI, which is basically probability that TI occurs in non-relevant document, is basically, you can understand this from the point of view of inverse document frequency as well. For a given collection, as I said, there will be a small fraction of documents which will be relevant, and the rest of the documents will be non-relevant. Right? Now, this SI, which is the probability that the TI is basically occurring in this set, that is excluding this relevance, can be actually considered based on its occurrence in the entire collection. This is a very important assumption. So basically, the entire collection is considered as the non-relevant set. Why? Because the relevance set is a very tiny one, a very fraction, a very epsilon set you can consider. So SI can be approximated by the entire collection. And hence the score of the document given the query could look like this. Here the constant PI is considered as 0.5. Here the probability of the term being occurred in the non-relevant document can be denoted by Ni by N, where N is the total number of document in the collection in C, and this is basically the document frequency of I, the term. So following this, we'll be ending up with this. If we do the maths, you can understand this part and this part will cancel each other. This denominator N will also cancel each other. So finally, we'll be ending up with capital N here for this one minus Ni, which is basically a document frequency of I divided by Ni. Okay.